The topics for this will be the wave propagation in the lossy dielectrics. Yeah, I think these are the things that we have agreed. Yeah, on the last chapter of EMT, is that the first thing that we have to do is that we're going to formulate the general equations based on the Maxwell's equation. Yeah, and then we're going to characterize the behavior of wave propagating in a free space and lossy dielectric. And then characterize the wave behavior in a lossy medium. Yeah, this is our present task, which is to discuss about the wave propagation in lossy dielectrics. And the last topics of this last final chapter is to characterize the wave behavior in a good conductor. Yeah. Okay, so for this, we're going to proceed. We're going to learn on how the wave behave on the lossy medium. So this topic of lossy dielectrics, we have learned this in lecture 22. So I hope that you can still recall the difference between the lossless dielectrics and also the lossy dielectrics. Yeah. Okay, so let's have a look at the objective. So a very straightforward objective here, which is to study the wave propagation behavior in a lossy medium or lossy dielectrics in terms of its intrinsic impedance and the velocity of the wave, the phase constant, and also relationship between the E field and the magnetic field. So the behavior are the same. Yeah, the behaviors of these waves are the same, except that the properties of the medium will distinguish the equations, the formulations that shall be applied in calculating those parameters. Yeah. Okay, so this is I can say this is just as a revision on the lossy dielectrics. We have learned that for the case of lossy dielectrics, the permittivity is a complex number. Yeah, it's a complex value in which the permittivity is consists of the real numbers, which is the epsilon naught multiplied with the epsilon r. And for the complex number, which is for the imaginary value, it should be the ratio between the conductivity of the medium and also the frequency, yeah, sigma over omega. Okay, I hope that you can still recall this, yeah, based on lecture 22. Or if you want to have more understandings on this issue, please refer back to lecture 22, yeah. Okay, so based on this, we can see that there should be some difference, yeah, there should be some difference between the wave equation, yeah, that have been applied for the case of lossless dielectric, yeah, and also for the case of lossy dielectrics. For instance, yeah, for instance, if we base on the K, yeah, the propagation constant, for the lossless medium, we have it as omega set of mu epsilon, right? Yeah, in which for the case of lossless medium, we have agreed that the epsilon is a real number, so we can have the value of K to be a real number. But when we have the epsilon, let's say for the case of lossy medium, here is a complex number. So if we base on this equation, we can now say that K will not be a real number anymore, but K will be a complex number due to the fact that the epsilon is a complex number. Okay, so this is a very direct effect when we are having the complex value for the epsilon, in which the K will also be a complex number. The same things apply for your impedance, yeah, intrinsic impedance. We have previously, for the case of lossy dielectric, impedance is given by set of mu over epsilon, in which for the case of lossless medium, epsilon is a real number, so that we're going to have, or going to get that impedance will be also a real number. But when we are having the lossy dielectrics medium, in which epsilon is a complex number, the thing is that your impedance value will also be a complex number. Yeah. So you can see that the effect of epsilon will be very much affected the value of phase constant and also the value of impedance. Yeah? So we're going to see later in this lecture what should be the difference, what should be the effect, or the effect of K, the effect on K, and also the effect on this intrinsic impedance or the eta parameters, yeah, when we are having the medium as a lossy dielectrics. Yeah. Okay, so this is the case. So we have learned that previously when we consider a lossless dielectric, the K is omega set of mu epsilon, yeah, and we have agreed that we are having lossless dielectric, epsilon will be a complex number, and as such K will also be a complex number. So when we substitute, yeah, previously we have epsilon equals to epsilon naught epsilon r minus j sigma over omega. Yeah, this is the value for permittivity for the case of lossy dielectrics. We substitute this in the equations here. Yeah, so we have omega set of mu multiplied with the permittivity of lossy dielectrics, which is epsilon. So just bear in mind that this epsilon here will basically equals to epsilon naught multiplied with epsilon r. Yeah, yeah, and we can take out this set of mu epsilon, yeah, from this equation. So we're going to have this k, equation number 3. Yeah. Okay, so we've clearly shown that the k, your phase constant, will be a complex number. Okay, and then from here, we are going to formulate the k actually. Yeah, we're going to formulate the k. So what I did here is that we assume that the k terms is written in terms of the alpha and beta. Yeah, the k, which is a complex number, is written in terms of alpha and beta. And our task now is basically to find out what is alpha and what is beta. Yeah. So this is the mathematical formulation, mathematical derivation for the alpha and beta. Yeah, I don't want to proceed with this formulation, the derivation. So you can try it on your own. Yeah. So these are the steps. Equation number 4, equation number 5, 6, and 7. Yeah. So I skipped this derivation. So I left this for you to derive this on your own. So the thing that I want you to understand is that the complex K is now written in terms of alpha and beta. And from the manipulation of alpha and beta here, finally we managed to get that the alpha and beta is written in equation number 8 and equation number 9. Okay. So alpha is given by these equations here, which is actually depending on the frequency omega, depending on mu, permeability of the medium, epsilon, which is permittivity of the medium. Okay, bear in mind that this epsilon is equals to epsilon naught epsilon r. Yeah. Then we have set of 1 plus sigma over omega squared divided by omega squared and epsilon squared minus 1. So this alpha basically is in the units of Nappers, yeah, Nappers per meter. Yeah, Nappers per meter. And the alpha basically represent an attenuation constant. Yeah, attenuation constant, right? Which is a measure of the wave attenuation while traveling in a medium. So basically, the alpha will be a parameter which determines how much the wave is said to be attenuated. Yeah, the wave is said to be attenuated while traveling in a lossy dielectrics or lossy medium. Okay, so before this, we have agreed that for the case of lossless dielectric, remember, for the case of lossless dielectric, we have agreed that the sigma equal to 0. Yeah, there is no, sorry, not alpha. The sigma, yeah, the conductivity equals to 0. So when the conductivity equals to 0, we have agreed that the JC, yeah, the JC is the conduction current, is also equal to 0. And we have learned from lecture 22 that this particular sigma, this conduction current, is the source of loss in your medium. Yeah, source of loss in your medium. So that is why if we consider the medium of loss dielectric, there is no loss occurred in a medium. So that's why if you base on the equation for the loss dielectric, we have a very nice wave. For instance, if you base on the E field wave, yeah, just for example, so we have E amplitude, the E naught cosine omega t minus kz, for example, the direction of x. We can see that there is no such loss occurred in the E field. Yeah, the E field is said to be uniform, a very nice uniform wave. from the end, from the start to the end. Yeah. But when we consider a case of lossy dielectrics, okay, lossy dielectrics, where we have the sigma is not equal to 0. Yeah, when sigma is not equal to 0, so the GC is also not equal to 0, and this will then incur losses in a medium. Yeah, incur losses in a medium, in which the losses of the medium is characterized by this value of alpha. So alpha will determine how much the loss will happen, the loss will occur in a wave propagating in these particular lossy dielectrics. So you're going to see that there should be no more nice wave equation like this. So you're going to see after this what should be the difference on the wave equation once we have the alpha in your medium. Yeah. Okay. Hopefully you can now distinguish the difference between the wave propagating in a lossy dielectric and the wave propagating in a lossy dielectrics. Yeah. Okay. Next is on the beta. So because we have agreed that just now that the Jk is composed of alpha plus J beta. Remember what is Jk here? If you base on the lossy dielectric, K is your phase constant. Yeah, K is your phase constant. Okay, and in lossy dielectrics, K basically is represented by beta. Yeah, K is represented by beta. So basically, in the lossy dielectrics, the K, which is the phase constant, is now separated or is now divided into two different parameters. The first one is the alpha, which is the attenuation constant. Second one is the beta, which is the phase constant. From the Jk just now, which is alpha plus J beta. Yeah, alpha is the attenuation constant and beta is your phase constant. Yeah, and alpha and beta, if you base on the equation, is almost similar, but the difference is only here. Here we have -1, here we have +1. So that is the only difference. Okay, you don't have to memorize, yeah? You don't have to memorize alpha and beta because alpha and beta will be provided to you in your examination. So you don't have to memorize this equation. Yeah, so it's very important to note that never memorize this equation. All of these parameters will be given to you. Okay, so back to this. So beta is a phase constant. So basically beta and K are the same parameters. Yeah, K is in a lossless dielectric, beta is in lossy dielectric. So these two are the same parameters. The difference is that the first one is in lossless medium, second one is in lossy medium. Yeah, so basically the phase constant is a measure of how much the phase change while traveling in the medium, and the units for this will be radian per meter. Yeah, similar with the K just now. Okay, yeah. All right. So now we're going to see how this particular alpha and beta will be reflected in your wave equation. So for this, we have to go back to this equation. So I think I have discussed these equations in the first lecture just now, and also in the previous lecture on Thursday, in which this is based on the equations that we have seen before. Yeah, basically this is from the equations of wave. Yeah, this is the wave in the positive z direction, and this is the wave in negative z direction. Yeah. Okay, so what we have to do now is that we have to substitute the equations of Jk, yeah, because remember that this equation number 10 is based on the wave equation in a loss dielectric because we are using K there. So this is for the case of lossless medium. And we have agreed in the previous slide that the Jk is alpha plus J beta, yeah, which consists of the attenuation constant alpha and phase constant beta. So we need to substitute the Jk as the alpha plus J beta, yeah, and we substitute in equation number 10, and we have obtained the Exz as in equation number 11, which consists of the Ex positive negative alpha plus J beta of Z, Ex negative E positive alpha plus J beta of Z, yeah, by just simply substituting or replacing Jk with alpha plus J beta. Okay, so now what we do is that we only consider the wave propagating in a positive z direction. So I can cancel out the wave in the negative z direction. So I just consider this equation here. So we're going to have it as Ex positive exponential negative alpha z exponential negative j beta z. So in its trigonometric terms, I can write the equation number 12 to be equals to equation number 13, where we have exponential negative alpha z multiplied with ex positive cosine of omega t minus beta z. Okay, so this is the equation of the wave. We compare this with the equation of the wave, electric field wave in a lossless dielectric. Remember, we have exz if we consider same uh, direction and the polarization, which will be ex positive cosine omega t minus beta z of x. So we compare these two equations, yeah, number 13 and this equation. This is for the case of lossless medium. The difference is that we can note that the effect of multiplication of the amplitude with exponential of negative alpha z, which show that in the lossy dielectrics, the amplitude of your field wave will be reduced exponentially. Yeah, the amplitude of the wave will be reduced exponentially. As compared to the lossless medium, there is no reduction of the wave. Yeah, means that there is no losses happen in your medium. Yeah, because we agreed that for lossless dielectric, there is no losses. Yeah, by the word lossless itself, yeah, there is no losses. But when we have a lossy dielectric, so lossy medium, the effect will be the amplitude of the wave will be reduced exponentially. So if we compare, if we see that, if you base on this equation here, for instance, yeah, this is the direction of wave, this is z direction. Initially here is the amplitude, which is at ex positive. So as the wave propagating in a positive direction, the amplitude will be reduced exponentially. And this is given by what? Given by multiplication of the wave amplitude at z equal to 0. Yeah, this is at z equal to 0 multiplied with exponential terms of alpha z. Okay, so the wave is based on this equation. The amplitude will be reduced exponentially because we have agreed that in lossy dielectrics, the E field equation will have the effect of this exponential of negative alpha z. Yeah, alpha is your attenuation constant. Z here is the distance of propagation. So basically, if we have bigger z, yeah, bigger z, the amplitude will be reduced significantly. Okay, then. Okay, hopefully you can identify the difference between the wave propagating in a lossless medium and also in a lossy dielectrics.
Doctor, why we not consider the ES negative part?
Exponential.
Ah,
Why
the
we don't consider?
the ES negative. Then you put a
Okay.
cross on that.
Okay.
And,
The thing is that this is based on the mathematical derivation we have. Yeah, because we are using mathematical method, yeah, to obtain these two equations of wave propagating in a positive z and wave propagating in negative z. Okay, but when we go into the practical application of the wave, we can assume wave only propagating in a single direction. So this is more towards real application where we assume that the wave is only propagating in one direction instead of two. Yeah, instead of return, we assume that the wave is only propagating in a positive z direction. That is our assumption. Is it okay, Wehan?
okay.
Yeah, no need to think about the wave propagating in negative z directions then, yeah, because this is just a mathematics. Yeah, the mathematics based on equation number 10, we can have both wave in a positive direction and negative direction, but there is no use to investigate further on a negative z direction because it's enough for us to consider only a single direction of the wave. Yeah. Okay. Hopefully you
And
understand.
the
Yeah.
ES and for the graph decrease exponential means the wave will reduce to 0, right? The ES.
End up. Yes. End up it will reach to 0. Correct.
0 means disappear the wave.
Yeah. Yeah.
Okay. Thanks.
Yeah. Okay. All right. So it basically the reduction of the wave reduction of the wave will be depending on your alpha, right? The degree of alpha. Yeah. So if your alpha, because we know that we have from this equation, yeah, Ex positive over E alpha of Z. So if alpha is very big, yeah, so we're going to have a wave will be reduced drastically as compared if we have smaller alpha. Okay, so that should be the difference. Yeah? Okay then. Right, this is in terms of graphic, yeah, the difference between the wave propagation in a lossless medium and also in a lossy dielectrics. And I hope that with this graphical image, you're going to have a clear understanding on the difference between the wave in a lossy dielectrics, also in a free space as compared to the wave in a lossy dielectrics, yeah. Okay, so in a free space in a lossy dielectric, the wave is uniform. There's no losses occurred in the wave, yeah, as we increase the distance or the distance of propagation. But when we have lossy medium, based on the equation itself, the wave will be reduced exponentially. Yeah, wave will reduce exponentially as we increase the distance of propagation. Yeah, right. Okay, and note that the equations here, K is represented or replaced by the beta. Yeah? K is replaced by the beta because we have learned that K and beta are the same parameters. Both are phase constant. Yeah. Okay. The alpha is the different because alpha is to be multiplied with the amplitude of your E field or H field. Yeah. Okay, so now we proceed with these impedance, right? Intrinsic impedance. We have agreed that for the case of lossless medium, because real value of epsilon, impedance also be a real value. But when we have a lossy dielectrics, due to the complexity or the complex value of the epsilon, the impedance will also be a complex number. Okay, so what we did is that we substitute the value of epsilon here, yeah, so that should be your epsilon value. Okay, and end up we can write that the eta or the impedance will be returned in terms of the amplitude and the phase. Amplitude and the phase, yeah? Yeah, because when we have a complex number, we can write it in terms of the phasor form. Yeah, we have the amplitude and the phasor. And then for this, we can write that the amplitude of the impedance for the case of lossy medium shall be written as this. You can prove this on your own. Yeah, don't worry, this will be given to you. You don't have to memorize this. Yeah, basically this obtained from here. Yeah, the amplitude derivation, and also the angle of theta. Yeah, the angle of theta will be based on this equation where we have tangent of 2 of the angle of theta equals to sigma over omega epsilon. Okay, so these are the two equations that enable us to find the amplitude of the intrinsic impedance and also the phase of your impedance. Yeah, phase of the impedance and also the amplitude of the impedance based on these equations. Okay, don't memorize these equations, yeah, it will be given to you. You just need to know that for the case of lossy medium, the impedance is now a complex value or complex number. Okay, and the next will be relationship between the E and H. Yeah, for the lossy medium. Yeah, what should be the difference between the E and H for the lossy medium? So due to the fact that the eta is now a complex number, yeah, because we know that the eta can be written as amplitude and the phase. This is for the case of impedance in the lossy dielectrics. So when you substitute it in the equations here, we can say that the ratio between the E and the H, which is known to be the eta, we can say that when we substitute the eta in these particular equations, we can say now that the E and H will not be in the same phase anymore. The E and H will be having phase difference. Yeah, we'll be having a phase difference in which the phase difference will be depending on the value of theta. Yeah, the phase difference will be depending on the value of theta. Evidently, it's shown by this equation here. Yeah, that when we substitute the eta as the amplitude and the phase, then based on these equations here, the H field is said to be always lag the E field by this angle of theta. Yeah, the H field will always lag, or in other words, you can see that the E field will always lead the H field by this angle of theta. Yeah, so that should be the things that you need to understand, yeah, based on the equations here. Right, this is your H field wave, yeah, H field wave, which is Hy positive. Remember, exponential of negative alpha z still there in your equation. The difference is only on the amplitude of the H field, which is given by the E field amplitude divided by the amplitude of your impedance. The angle of theta has been substituted in the angle here in the cosine terms. Yeah. Okay. Okay. So this is the graphical graph that represent the field of E and H, in which we can see that the E field will always lead the H field wave by theta angle. Yeah, theta angle. Okay, then, and finally, this will be the velocity. I think there should be no difference at all. The V will be equals to omega over K, yeah, in which we have the K equals to omega divided by V, or velocity. And for the case of lossy medium, K is beta, so beta will be omega divided by V. So the rest will be the same, yeah. We just change the K with the beta, but to find the velocity of the wave, yeah. Okay, so for the case of wave propagation in lossy dielectrics, I think two things that need to be observed, two important information need to be observed. The first one is the field, both E and H field, yeah, the E field and the H field, both of them will be attenuated, yeah, will be attenuated by these factors of exponential negative alpha z, yeah, will be attenuated, yeah. And next, number two is that the E will always lead the H by this angle of theta, which is the angle of intrinsic impedance. Yeah, so these are the things that you need to observe. You need to distinguish between the wave propagation in a lossy dielectrics as compared to the wave propagating in a lossless medium or in free space medium. Okay, the first one is the attenuation of the wave. Secondly is the phase angle difference between the E field and the H field wave.